I'm Jody Hagins, and today we're going to be talking about polymorphism, cohesion, and coupling. Oh my, from Wizard of Oz. Now, this title is a little bit deceiving because while we will talk about polymorphism, we will talk about it in a way that you might not have seen before because it's not about virtual functions. It's about something taking many forms. This talk is how many of you saw, this was my talk last year at cppcon? Anybody seen this? A few people, okay. So that means that I will go with option A, which this talk is part 2 of that talk. So I will basically spend the first part giving a summary of that talk, which is basically how to use modern C++ to be able to take advantage of compile time optimizations for a design from 1984 that requires a lot of runtime checking. And so we want to get rid of all the runtime checking. The thing that it allows us is to be able to reduce coupling and increase cohesion. And it does this through the common tool of polymorphism, which is why it's the title. I'd be remiss if I didn't at least mention this book, Multi-Paradigm Design for C++. After my initial love affair with implementing kernel streams in C++, this book came along probably 1998. And most of the design principles that I'll discuss, most of the design principles I try to follow can be found in this book and likely numerous others. He says a couple of very important things here with my little addition. One goal of design is to minimize coupling between parts and to maximize cohesion within them. My modification is that one primary goal of design is to minimize coupling between parts and to maximize cohesion between them. So what is this coupling and cohesion? So there's a computer science class from Washington University, and this is actually on their syllabus. An indication of the strength of interconnection between program units. Well, what are program units? Highly coupled have program units that depend on one another. Loosely coupled are made up of units that are independent or almost independent. And modules are independent if they can function completely without the presence of the other. So this is the idea of things that have dependencies on one another. How tightly coupled are they? Do these dependencies, can they come and go freely? Or once they're made, are they formed in concrete? Cohesion is an indication of the strength of the interconnection between program units. Basically, a component should implement a single logical function or a single logical entity. All the parts should contribute to the implementation. So the cohesion is how concise your implementation is, how tight it is. Coupling and cohesion are like opposites. They fight one another. So one goal of design is to minimize coupling between parts and to maximize cohesion within them. So cohesion is how much one part of a code base forms one program unit. And so what do you call a program unit? Coupling is how much a single program unit depends upon other program units. Typically, we talk about program units and we would think of classes, or we might think of functions or files, right? They're program units. I want to kind of challenge your thinking and get you to think of program units as blocks. A block of code is a program unit. Why do we not want to have functions that are 5,000 lines long or 500 lines long? Or maybe even 50 lines long. Functions, the idea of cohesion is that something has one task and it does that one task. This is different from the single responsibility principle for classes, because a class doesn't necessarily just do one thing. It's supposed to have a single responsibility, which may be managing something that has several different things that it's going to do. But really, a function or even a block of code should really be doing one thing. This is easy to do with blocks. It's not necessarily easy to do with other things because you end up paying overhead for them. Typically, the reduction of coupling and the increase of cohesion is accomplished through polymorphism. Now, what is polymorphism? It literally means multiple forms, right? It comes from biology. I'm not a biologist, but where a species may have multiple forms within the same area. And so you have something that takes multiple forms. We see this in C++, where you have a class that has virtual function foo, or a virtual function draw, and everything that inherits from it has a different type, and then they implement that draw. They have different forms. There's multiple of these forms of the same thing, the same draw. In programming language theory and type theory, polymorphism is the provision of a single interface to entities of different types, or the use of single symbol to represent multiple different types I added of behavior. This is from our famous Wikipedia, okay? Take it for what it's worth. But it means something to me, because that's pretty much exactly what we're trying to do. And in most things that you want to do in computer science, where you're trying to reduce the coupling between things and increase cohesion, you're doing some form of polymorphism, whether you think about it or not. So I want to tell you about a design that I love that's been around since 1984. And not a whole lot of people use it. I don't use it as much as I want to. I've tried to use it everywhere I've been since the 80s. The reason that I can't use it as much as I want is because of performance. It has a lot of overhead. But it really is nice. So I want to talk about it. But in order for you to understand why I love it, I want to talk about this, journey before destination, with an apology to Brandon Sanderson. The most important words a man can say are, "I will do better." These are not the most important words any man can say. I'm a man, and they are what I needed to say. The ancient code of the Knights Radiant says journey before destination. Some may call it a simple platitude, but it's far more. A journey will have pain and failure. It is not only the steps forward that we must accept, it is the stumbles, the trials, the knowledge that we will fail, that we will hurt those around us. But if we stop, if we accept the person that we are when we fail, the journey ends. That failure becomes our destination. To love the journey is to accept no such end. I have found through painful experience, the most important step a person can take is always the next one. This is a great novel, and I don't want to demean it in any way, but this has kind of been my journey. I've been on a quest for something that accomplishes these tasks and gives me the performance that I want. And I've failed time and time and time again, which is why this paragraph means something to me. I will quickly go through this part here. There's a three-way love affair between System 5 streams, C++, and this guy. And if you note something strange there, that red box, that's kernel space, because that's where System 5 streams live. There's not really a good alternative for streams in user space. There's a couple we'll talk about later. But here's my beginning as a math major at the University of South Carolina In the 1980s, the early 80s, I was using Pascal on punch cards, and sometime I think in 1985, one of the guys in the math department got Seafront running on one of the PDPs. Can't remember if it was a PDP-7 or a PDP-11. And so I would much rather be writing C code and C++ code on the PDP than Pascal on punch cards with the IBM 360. And so that's where I first started falling in love with C++. In grad school, I was basically I was researching AI. Those are my papers that I published in less than 10 months. And then I won the lottery, I got married, I got out of grad school, and went to work for these guys writing Unix kernel code, which was my first foray into C, real C. We did what we called objective C, not objective C as what came to be known as objective C, more object-oriented C, where you take structs and you have functions. The first argument to every function is the pointer to the struct, different, things like that. So I asked, why can't we write C++ in the kernel? I mean, after all, at that time, we had Cfront. Familiar with Cfront? No, a couple? So here's how C++ started, is kind of like what Herb is doing with CPP2. So you would take your C++ code and you would push it through Cfront, and it would transpile it into C. And then you would compile your C code. And so that's how I learned C++. And it was a great way to learn. I really wish Cfront or something like it was still around, because it helped me a lot understand underneath what was going on. So I'm like, well, why can't we do that? And I'm like, nope. So I still had a dream of writing Unix kernel code in C++. I spent some time there, got to do some C++ underneath because nobody stopped me. And then I went to work for Siemens Stromberg Carlson, which was a telephony company. And this is where our story gained some steam. They were trying to build a system, and they had a demo when I basically started work there. And they had a demo that they had just successfully demonstrated like the week before. But it ran on one Solaris machine, and it was completely distributed amongst a lot of processes on that machine. Their next project was to distribute this across a bunch of machines. So they were going to redesign and rewrite it. So the goal was to take a set of applications running on one host, and the features, basically take this existing application and distribute it across a number of hosts, right? So this application was running using System 5.4 semaphores, shared memory, and message queues. The goal was to distribute it across a bunch of machines. And they were gonna have to rewrite and redesign their code. Me being a snot-nosed young kid, only out of school for a few years, told them that I thought we could do something else. Basically, add a feature, basically distribution of the whole thing with little or no change to the existing code. I told them, here's what we can do. We can take these calls. These are System 5.4 message queues. These are System 5.4 semaphores. This is System 5.4 shared memory. Fortunately, we didn't have to deal too much with shared memory. But what are these? They're all system calls. Remember earlier I was talking about polymorphism? Multiple forms? What's a form of polymorphism that we don't think about much? Link time, yes. Thank you. Link time polymorphism. So my idea was replace the implementation of all of these system calls, put them in a library, put them into the linker, because the linker is going to find the library functions before it ever tries to find the system calls, and it will link the code for the library calls. And now you have replaced all of those system calls with library calls. It's pretty easy to do. Take those. There's the APIs, pretty small, not a lot. We can relink, and then we're done. But we still have to implement them, right? We have to implement them so that they can communicate across the network. System 5.4 streams was written to provide fundamentally network access. When you open up a stream, you would open up a device driver, and on top of it would get pushed your Ethernet driver, your Ethernet module. On top of that would be your IP, and then on top of that, TCP, and then you open your port into the kernel, and now you're talking TCP back and forth. If you wanted a UDP stream, you would open the exact same set of streams. Everything is identical, except instead of putting a TCP stream on top of it, or module on top of it, you put a UDP module on top of it. So I wrote a kernel streams module that we called DCOMS. And I lost myself here. All right. So without talking about the DCOMS things yet, I jumped ahead of myself. We were able to implement these things. And it was a stunning result because we had link time polymorphism. We didn't even have to recompile a single line of code. We didn't have to touch a line of code. We didn't have to recompile a single line of code. All we had to do was add libdcom onto the link line. And now everything used the new code. We added a feature, and we didn't just add a minor feature. We added a feature of distributing our entire application across the network without changing a single line of code. All we did was add code. This made me fall in love with this idea. Not only that, I didn't have to change the protocol stack. I didn't have to change a network driver. I just had to write one streams module, push it on top of the network in order to do my distribution. So you want to have a distributed message queue? Fine, send me your function call. I will do all the plumbing across the network underneath. Nobody ever has to know. And it just all happened kind of magically. I say magically, but it's really not. It's just polymorphism. But we didn't have to change a single line of existing code. It shouldn't surprise us because we've been talking about this. And so, I guess, yeah, there. Did you notice the polymorphism? The polymorphism was link time polymorphism. It is a thing. Just add the same names. I didn't have to change any other code, but I got completely different behavior by linking to a different library. So I was in love at first sight with System 5 streams. The way that they work is you basically have a stream head, which is in kernel space. And then you have some number of streams modules that are pushed on top of some sort of streams driver, which could be a device, or it could be like a pseudo driver, or it could even be a loopback. Now, each one of these modules that you put on top of one another, I basically just wrote a DCOM module and pushed it on top of a TCP stack or on top of a UDP stack. How could I do that? This same concept of polymorphism. Because every module that you write, you provide a function called put. And what happens is the next guy, you have a message queue. He puts a message queue on. You can either take it immediately or it can get deferred and processed later in another thread. But it's the exact same interface between all of the modules. That is polymorphism. The problem is that the polymorphism that you have to do is every time I see a message that comes in, I have to examine it at runtime. And I have to determine, is this message destined for me? If it's destined for me, then I will consume it and I will do something. I may send another message down line. I may send a message back up front. I may just wait. I may update some state in my state machine. If it's not destined for me, and this is crucial, I don't reject it. I don't send back an error. I just send it to the next guy. I can't do anything with this. Maybe you can. And I just silently send it to the next guy. This is a very powerful mechanism. So the way that these messages work is you have their streams are bidirectional. You have a write side and a read side, or what's called downstream and upstream. And Messages just flow both ways. Here's a list of Streams resources. If you want to go look at them, this is a really good kind of like a reference manual. This is a really, really good manual, very hard to find, as is this one. This one is probably the best, mainly because it actually describes all of the functions. I took one summer with this book, Stephen Rago's book. He describes them in such detail that you can actually write an implementation of Streams just based on his descriptions of how things work. And you get 99.9% there. Really good. Doug Schmidt's ACE framework has a set of user-based streams. You can play with them if you want to. You're not going to get a whole lot of great performance out of them. This C++ networking book is similar, about the same, the ACE streams. And they basically implement this type of thing. So let's see an example real quick. You basically take a message, you push it through the stream head. You have some type of line discipline, and then a message can go back, or a message can go down. They're bidirectional. Once it gets to the driver, it can go back to the other side and go all the way back up to the server process on the other side. Does that make sense? And by the way, please interrupt me with a lot of questions. I changed the implementation to something that's much easier that we'll be looking at in a little bit, and I lost a fair amount of time, so I have plenty of time for questions. So this is basically TCP and UDP in streams. There's your TCP module and your UDP module. Notice they're at the same place. And then below, we've got the IP device driver, which is what's called a multiplexer in Streams terminology. It's a multiplexer because it services multiple things. You can have multiplexers that go one to many. You can have them that go many to one. And so you can create these T's and Y's in both directions in order to have multiplexers that can handle multiple streams. So remember that library I was talking about that we built to do we distributed the system. Well, once you have distributed systems working on the network, especially back then, this was probably 1991 maybe, maybe 92. You need reliability. And you need multiple network cards because you need to use the available network cards that you have. Back then, really, our systems were just, those coax cards. You put a bunch of these Ethernet cards, you put those in there. I think we could put up to 4 of them, and then you have wired coax that connects between them all. And that was our network. Well, these cards died. Somebody tripped on a wire or something went wrong, and we needed reliability. And so what we needed to be able to do is we needed to be able to add retries. We needed to be able to add reliability. We needed to be able to say, I have 4 connections. What I want to do is if I lose any of them, I still want to be communicating. And I don't want my connections to go down. So this library, DCOM, is the one we were talking about earlier. It was implemented in C++ and Streams. And so that library is what was doing all of the communication across networks. So we have several options for a solution here, right? We're trying to design our solution. What do we want to do? Well, that's where DCOM sits, basically. DCOM sits above the UDP module. That's a stream right there. Well, we could add recovery to it. We could update DCOM and add recovery to it. That's a reasonable solution. We could also have a separate recovery module, which is kind of better, right? We want to have things as loosely coupled and as cohesive as possible. Remember, our goal is we want to add recovery and we don't want to change any code. It's a new feature. Add a new feature, change no code. That's kind of the mantra. So we could add recovery down here, and if we added recovery as a separate module, we don't have to touch decom. But if we put it there, we may as well be able to bring it right down here underneath the IP module. And just have, because all it determines is what protocol is it talking back and forth. Well, if we could put it there, then why not put it here? Why not put it right above the Ethernet drivers? And configure the system so that every time a driver gets pushed into the system, the recovery stream gets plopped right in the middle, and all the rest of your network stack gets put on top. Surely that won't work because something's gonna break. Well, no, that's how it was designed. It was designed so that you could have modules of code and put them wherever you wanted, as long as they could talk with the people in between. And so now what we have is we have decom, which was the library that did all the distribution, and we had recovery, which was called, it was called Venom. I think it stood for Virtual Ethernet Management or Virtual Ethernet Module or something, I can't remember. But that's what it did. And so we have reliability. Well, what did we get? We got exactly what we wanted. We got reliability and light of hardware failure. Now, because it was implemented on all of those things at the Ethernet stack, at the Ethernet frame layer, it wasn't just reliability for stuff that was using the decoms module. The test application was just FTP. FTP, humongous file from one node to the other, and watch the hashes go, go, go. Go back behind it and start pulling cables out. And it's still going. The algorithm actually was a round robin algorithm. So you were actually able to use all 4 Ethernet cards at the same time for different packets. It was just round robin. So we got about a 3 times improvement in throughput because as long as none of them died, and as soon as any of them died, it just started falling back and falling back and falling back. And you just go and start unplugging them all and plugging them all back in, and everything on the whole machine worked that way. Now, I didn't change a single line of decom. I certainly didn't change a single line of the Ethernet driver. I didn't change a single line of FTP. I just added a piece of functionality and inserted it into the right place, and everything on the box got a performance win, and everything on the box got reliability. Failover. So we got sometimes performance, didn't change a single line of code in our applications, and this shouldn't surprise us because this is the goal of design, right? The goal of design is to minimize the coupling between things, the things that have to change, and maximize the cohesion by giving things single responsibilities, giving them small tasks to accomplish, and then putting them all together through composition. That's what the streams framework is awesome at. So what's the polymorphism here in the recovery? For the decom stuff, the polymorphism we got was link time polymorphism. What's this polymorphism? It's the interface between the streams modules. Every single one of them just has to have a put function, right? You have, it's actually like a vtable. When you build one of these streams modules, you fill out a table with functions that it's gonna call for certain things. It's just like a vtable. And that's the polymorphism, is that whenever they're just putting a message to you, and you have to look at the message and determine, is this mine? If not, give it to the next guy and let him deal with it. That's how the recovery was able to do its job there, because it only dealt in certain messages. All the rest of them it didn't care about, and so it just passed them back and forth. It's one of the great things about this streams design. So we want nice polymorphic interfaces, but it doesn't mean virtual functions and inheritance, because none of that was there, except for the streams module, which was virtual functions in C, right? Because it was just a table of function pointers. You want it to be easy to compose. You want to have low coupling, high cohesion, but there's a performance overhead for these features. These features don't come free. And so I did this stuff back in the early 90s. And ever since then, I've been trying to use streams like this, write my code this way, so that I can make changes, add a new feature, I shouldn't have to change a thing. I should just be able to add a feature and put it in the right place. I've had various levels of success. Modern C++ gives me the tools to have much, much better success. In fact, modern C++ gives me the tools to have exactly what I've always wanted. And that's all of these things and performance. Now, C++ 20 makes it much prettier, much nicer, and compile way faster. But the library that I'm working on is C++ 17 because we have to give our code to our customers. We provide our code to our customers and they have to have licenses. So we're kind of stuck on C++ 17 right now. Hopefully that will change, but not right now. But 17 is good enough to give us what we want. I will propose in a minute a design that allows us to achieve all of these things and all of that determination of the overhead of the virtual function calls, the overhead of the queues, the overhead of every single module has to examine some opaque piece of data and say, is this a message that I recognize? And all of that has to happen at runtime. And I will propose a design that allows us to do all of that at compile time. So that by the time you're done, you still get all of these benefits. You don't sacrifice one of them. But it all happens at compile time, and so you pay none of that performance overhead. You do have to deal with templates. You do have to deal with some metaprogramming. Hopefully the library will take care of the vast majority of it. And that's what we're gonna look at next. Before we do, this is my favorite slide. This is my favorite slide ever. This is from Howard Hennett's talk back in 2014. The last time I showed this, someone commented that, oh, we don't need that anymore. But that's the furthest thing from the truth. I challenge you, if you think we don't need this anymore, go look at any random code review pull up and find, has someone defined a destructor? If so, they've broken move semantics. You can move, it'll say it's movable, and you can actually even std move on it. But it'll call the copy constructor and the copy operator, the assignment operator. So this is the most important slide that I've ever seen. So I show it every time I give a talk. Any questions so far? Please interrupt me if you have them, but anybody got any questions so far? Maybe you think I'm just feeding you a pile of BS or something. All right. This was an example from the talk that I gave last year. There's some things to note about it. Can you see that? That's pretty, isn't it? So the comment that I made last year was that this library is difficult to use wrong. That's a good thing. Making something that's difficult to use incorrectly is a good design goal. Unfortunately, it's even more difficult to use right. Because all of the determination of whether you wanted something all had to happen in every single one of these little modules. Every piece of code you wanted to write to do this you had to implement your own spine. You had to basically enable and disable it. You had to add and remove tags to know what was in and what wasn't. And so I'm gonna walk you through this real quick so that you can see the idea of what's happening. So basically what you do is you can actually give this check flag lambda, you can give it to a stream. And the way that you build these streams up is using the pipe operator. You say, I have a stream and I'm gonna pipe into it, check flag, right? It's just something there. And what does it do? Well, this is just a framework thing, and it'll basically take any event, and what it does is it checks the tag of this event has compression flag. The example was, we have a protocol, they changed the protocol on us and said, hey, this particular bit in this message now tells you whether the whole thing is compressed or not. And so you have to implement that, right? So this basically says, in order to do things at compile time, you have to have types. So we tag it with has compression flag. Yeah, this thing has a compression flag. Somebody earlier has determined that we're gonna have a compression flag. Either you know it because of the port that you got on, or you know it because of the date, or you know it because of some reason. But somebody has done, see this add tag thing? Somebody has done that here. So if, when I get called, I have a compression flag, that's equivalent to getting an opaque number of bytes and looking at the first one and saying, is it the enum has compression flag, right? Then this will be enabled. And so the framework basically takes all of these streams, and every message it gets, every function call it gets, it looks at the first stream, the first module, and it says, can I call you with this? Can I call you with this specific piece of types of information? And if I can, I'm gonna call you. If I can't, what's the model of streams? Pass it to the next guy. So the framework itself will say, can I call you? If I can, I'm gonna call you and give you this information and you can do something with it. If I can't, I'm gonna go to the next guy. Can I call you with this? So let's assume that you can. Let's assume that I do have one of those things. Okay, then now I'm going to say, should I compress this event? And if I can, then I have to remove this has compression flag, because I now no longer have the compression flag, but I still have to manually remove that so that the next guy down the line doesn't see has the compression flag, because I'm going to decompress this stuff. And then I have to add a tag saying it's compressed, right? You get where this is going? You're basically manipulating these types so that people down the line can know what you're going to run. And then I will put that, right? So I call put next with the framework, and this framework is passed in by the framework. The framework is passed in by the framework, and it has all the template, all the metaprogramming magic. And it will basically do all of these things, and then it'll say put next with this. And then what it'll do is it'll look at all the things after here, and it'll say, hey, can I call you with something that has this event, and it has a compressed type tag on it? And if so, then it'll call it, okay? So that's kind of how this works. I'll tell you, everybody thinks their babies are beautiful. This is my baby, and it is ugly. It is ugly. I don't like it. So what I did is I had prepared this talk with the details of an implementation using that syntax. While I was doing the talk, I hated it so much that I went and changed the library to get rid of it. You can still do it because you need to do that for powerful things. But most of the things, you don't need it. So what we're gonna do is we're gonna see an example, and we're gonna walk through an example of an implementation of how you can do something like this. What we're gonna do is we're gonna use as an example NASDAQ total view itch. For those of you that don't know much about the financial data, this is basically the NASDAQ stock market. This is their data feed. This is how they send their data feed out to people, right? So every time you want to buy 100 shares of Apple on NASDAQ, they will send a message out to everybody on their data feed saying, hey, somebody just placed an order to buy 100 shares of Apple at $4.97, or I have no idea what it is right now. And every single event that happens, all the events that are considered public get sent on this public feed. So this is their protocol. And so what we're gonna do is we're gonna implement part of this, okay? Last year I implemented a very small toy, and people were like, yeah, why would you even do that? And it's right, if that's all you're gonna do is have one function and mess with it, you probably shouldn't do this. So this feed is made up of a series of sequenced message. Each message is variable length. So the message comes and it just has a length part that tells you how many bytes are in the message. Okay, make sense? They're typically delivered via a higher level protocol that takes care of sequencing and delivery guarantees, right? So they're sending you a bunch of messages, and the messages are supposed to be sequenced. In other words, you need to be able to process message, you need to be able to process the buy for Apple before you process the trade that happened. and they sequence them. So they guarantee this sequencing through a couple of different protocols. The first one is called soup bin TCP. And the next one is compressed soup bin TCP. So soup bin TCP is basically you connect a TCP connection to a server, and you issue some login, and you start receiving messages. You can tell them, hey, I want to start receiving messages at, message 1 million or whatever. But then you just start receiving messages. And you start receiving these application sequence messages. I can't see it up there. It doesn't show up in the white. You start receiving those as part of your TCP feed, okay? The compressed one, they compress it first with zlib compression. So they compress it before it goes onto the wire. So you're supposed to uncompress it before you start processing it. And then they have one called mold UDP 64. UDP, it's an unreliable protocol, but if you're co-located, most of the time you're not going to lose messages, and most of the time you're not going to get them out of order. But you can. It's an unreliable protocol in that they send you a message, and it will come through the network, and it might get lost. And if it does, there's no, like TCP has basically the same thing underneath, but the TCP protocol recognizes if it's missed stuff and sends back to the other side saying, hey, I missed this message, send it back to me. But these UDP packets, and they'll send you a packet. So that's what the mold UDP 64 is. It sends the exact same messages, but they're just wrapped and sent through mold. So the soup bin TCP client is what you implement in order to read these messages. It has a 2-byte big endian length that basically tells you how long the message is. It has a single byte header, which indicates the packet type. So it's got 2 bytes, tells you how many bytes are coming. The next byte out of that is something telling you what this message kind is. And then the rest of it is just the rest of the bytes of the message, right? Now, it's important, it says that the length of this byte, the length of the 2 bytes isn't included in part of the message, right? So you read those 2 bytes, it says 20, you know I should look at the next 20 bytes to figure out what my data is. So what we're gonna do is we're gonna add some protocols for soup bin TCP. We wanna write a simple module. And what we want to do is we want to add some protocol tags. Remember those tag things? We want to be able to determine things at compile time. So what we want to do is just add some protocol tags to this TCP thing. So we just can write this lambda for add protocols that takes the context, and it takes some bytes, just some general bytes. Bytes is basically just implemented in terms of basic string view unsigned char, right? It's just a view over some bytes. And then it takes those bytes and it puts them to the next thing. And it also includes these tags. These tags, they're types, but they're values, right? Now, I'm using a syntax that doesn't work on Microsoft, but I'm not that concerned right now. C++20, you can do some other things, and this was just easy. It's easy to read on the slide, okay? And this works. Maybe Microsoft allows this now, I don't know, but GCC and Clang have supported this for a really long time. So what this will do is this will create a special type NASDAQ stock market venue. That's a special type, okay? This soup bin TCP protocol and total view protocol, because those are the protocols that we're using, right? It's the NASDAQ stock market for these. And so we're gonna put those to the next module. So soup is a TCP protocol, and when you read TCP protocols, you have no idea what you're gonna get. You just get some number of bytes. It may be 20 messages. It may contain only part of one message. You really don't know. So what we'll do is we'll just write a module that streams these things. It's not super efficient because it's an example, it's slideware. I don't advise you to use just a vector for doing this. You should probably use maybe a circular buffer or something even better, but this is what we're gonna do. So the put member function. Previously, we used a lambda. So the framework itself, it uses polymorphism, and it treats a member function named put or a call operator, or a callable object. It treats them the same. It does some metaprogramming to determine what they are. But if you have if you're callable, then it'll treat you that. If you have a put member function, then it'll use your put member function. And we'll see later why there needs to be some distinction. So here's our put, and we're saying that there's the CTX, that's just our framework context, because the framework is always calling us. You put bytes into the framework, into the stream that you create. And then those bytes, the stream manages. It's pretty simple. It just walks down the list of things that you've composed and says, can you take this? No. Can you take this? No. Can you take this? Yes. And it'll call it. And it does that at compile time, okay? So, and notice this here. It takes the decal type of soup bin TCP. So this function, remember the long thing that we had to do with the decal type in that example earlier where we had to say decal type, do you have this compression flag? Well, this is a tag that we're just passing as a value. And so the framework will just match this tag. This function will only get called if it has a parameter of bytes and it has a type or a value of this type soup bin TCP protocol. That's when this one will get called. Remember the stream that we showed earlier. It's like passing the message through. That's the only time this will get called. It doesn't matter where it is in the stream. You can pass stuff through, and if it's not one of these, it won't even get called, and you pay no runtime cost because it gets filtered out at compile time. Okay, any questions about that part? All right. So basically we just and we're just putting the stuff at the end of a buffer, that's nothing. And then we're basically, do we have enough bytes in the buffer to actually have a message? If so, we go load it. We call load because documentation says this is big endian, so we have to do that big endian conversion. And then we basically just figure out what our message is, right? And we say, now I've got a message that I'm going to put to the next side. And I do a put next of my message. And my message has the buffer data and the total. Okay, and then I'm gonna erase the part out of the buffer. It's gonna be erasing out of the front of the buffer, so that's not very efficient, but yeah, we don't care right now. Okay, any questions about that? So it's basically just taking some number of bytes, ripping through, finding where they are, and sending a message every time it finds one. Yes? Yes, you can place, yes. The big thing with C++20 is these things that you have in here, kind of like think of senders and receivers. Sender is a concept. So you can actually put concepts in here and make this much nicer, and it makes the metaprogramming much better. Because I'll tell you what happens. If you noticed earlier, I don't know if you remember, but back here, what did we actually put next? We put next this thing with bytes and all these things. This function here just takes one protocol. And so the way that the framework works is that if you match at all, it'll call you, right? So if you got extra things, because those are the extra tags that you still need to pass along. And so what the framework will do, it takes all these values that you've had, and to make this nice and pretty, it actually, okay, yeah, I'll confess, it's an n factorial algorithm. So don't try to pass 20 parameters, at least not yet, because I just implemented this part of it. Because basically all it does is it does a permutation. It says, here, I've got all these parameters, and it creates at compile time a permutation of all possibilities of making a call into that function and picks the first one that works. If I can call it with it, then I'll call it. The very first parameter is treated special, but that's basically what it does. And so in this case, because bytes and soup bin TCP were two of the types that were in there, it'll get called with those two types. But what happens to the rest of them? The framework keeps them because it'll get passed to the next time. Whenever a type is taken, bytes and soup bin TCP, they're considered to be consumed. This function has consumed them. The framework still has the things that it didn't consume. And so what'll happen is the next time, right here, when the framework calls put next, right here, this thing's not working, so right here, this put next, the framework has a list of all the things that it was given originally or that it's built up over time that this guy did not consume. So this will get added to that list of arguments for the next call. The ones that got consumed, they're no longer there. If you want those to be consumed again, you have to put them explicitly. So this gets around, remember all that add tag, remove tag, is tag, all that stuff? This obviates all that. It gets rid of all that stuff. It makes it much nicer at the expense of more difficult framework and much slower until I come up with a better way of doing this. It's kind of hard actually because anytime you have functions with template parameters, you can't really deduce those types. And so it kind of becomes hard as far as what you can pick out. But if any of you guys have done this and have a good, efficient algorithm for it, please let me know. That would be awesome. We already did this, didn't we? Yep. So here's our soup bin TCP. Here's what a logical packet looks like. Oh, did we do that? Yeah, so we just talked about that. So we have a soup bin TCP message. This is what it looks like. It's a 2-byte packet header with a packet type and a variable payload. And so what do we have? We have a parser that's basically going to take a soup bin TCP message. That's what the last thing gave us, right? It looked at it and said, oh, because it was just doing streaming stuff. I have a full message, I'm gonna send you a full message. Now we take this full message and we basically just switch on its message type and we put next a sequence of bytes because capital S means sequence. Plus means debug. There's like a dozen of these and I didn't want to put them all on here. But basically you write a switch statement or you have a code generator that reads the definition of the protocol and generates the switch statement for you or generates the dispatch for you. And so we're basically then just going to put next these sequenced bytes. So note that this soup bin TCP message, which we got in, it's been consumed. So it's no longer, the framework isn't gonna put it next. What's gonna be put next is the things that haven't yet been consumed and this sequenced bytes with a sequence number and a payload. Okay? On the TCP, every message has a sequence number that starts at 1 and they implicitly increment by 1 for every message you receive. These messages on TCP are not sequenced. Why do they not have to send us a sequence number for them? Sorry? Yeah, TCP will guarantee that we'll get them in the order that they were sent. So we don't have to, we just implicitly increment by 1 every time we get one of these sequenced messages. They also have unsequenced messages that they'll send, and they have debug messages and log in and log out. So you still have to establish a connection, but it all basically works out the same. Okay? Now, this is what a NASDAQ stock exchange application message looks like. For all of the messages they define in the document, something like this, where they'll tell you the first byte is going to be the message type, and then the rest is going to be a fixed number of bytes that they tell you what they are. And by the way, this document is publicly available. I think I had the link on the very first slide, but I'm not sharing anything. I mean, it's on the web. And so this message has a message type of S, and it has a size of 12 bytes. And it's a system event. So we could write a module that examined the type and size and delivered a type-specific message to the next module, right? So this is our module that'll dispatch total view messages. We've got our framework context and just some generic bytes. And now we're looking at this total view protocol, right? This will only, how do you prevent this from getting called with just any set of bytes? Well, this is how. It'll only ever get called if it sees a set of bytes and in that glom of things that it has, of arguments, one of them is total view protocol. Okay, and so this will get called. And basically we then just put a total view system event. Okay? Now, we really don't know who's next in line when we call this put next. We don't really care. Because our only job is to do what we're supposed to do. Now you think about this. We could have written one piece of code, one class with a bunch of member functions, a bunch of other stuff, or we could do something like this, which is composable. One of the reasons for making this composable is, well, let's say that someone has a file and they just save the messages. You want to read the file. Well, you can just read that file and send them to one of these guys. Everything is broken down. And what it means is every single one of them is extremely easy to test. Every one of these modules has a defined input and a defined output. And most modules you write should hardly ever have more than like one or two if statements. I try to have none. Some of them we will. We'll see in the UDP. Thank you. Okay, but one of the things that we want to be mindful of is that our goal is not to play with template programming. Our goal is not to play with things. Our goal is to build a system that is very loosely coupled, has tight cohesion, is extremely testable, and composable. And this meets all of those requirements. I can add a feature without making a change, just like we showed earlier in the different versions of polymorphism, right? I can add a feature and not make a change. It's part of the single responsibility principle in object-oriented design. I should be able to add it's open-closed, right? Open-closed. I should be able to add something and then go in and change it by just re-implementing this virtual function. And I've kind of added a new feature. I've changed something, but I haven't changed any other code. So that's our goal. And if that's our goal, we should not be making these monolithic implementations of our modules. Our modules really should be small, very testable, very composable. And if you find that, oh, these things are kind of small, they always go together, well, just put them together. There you go. There's soup. Soup is a stream head with add protocols, stream parser, message parser, and the dispatch. Now, if you notice earlier, some of these were lambdas. So you could write inline lambdas here if you wanted to. But if you write inline lambdas there, how are you going to test that inline lambda? Right? So I want to give names to things so that I can test them. And now I've got soup. Okay, any questions about this? Yes?
What does the context do in all this? Where you call context to put next, what happens inside there?
I'm sorry, one more time?
You've got context to put next. Slides. Like what happens inside?
Okay, sure. I'll go back. Okay, the question is, we've got context.put next. What happens inside there? All right, so this context put next, this context came from up there. It was given to you by the framework. So in here, you've got soup. You would basically do soup.put something, some number of parameters. You do soup.put some number of parameters. And then the framework takes over. The framework then looks at the very first thing in the stream and says, can I call your either put or your call operator? And if it can, it calls it. Okay? But once you're inside there, what's and put next is similar. So what context.put next does, it tells the framework, put these to the next guy in line. So it says, hey, framework, take these parameters, take this parameter, which is just this system event, combine it with all the things that you still have in your reserve of stuff that you're sending along, and call put next on the next module that allows it. So at compile time, it will look at the next module and say, can I call you with some combination of this and the things I have? If so, it will call that module's function. If not, it'll look to the next guy in the list. It keeps a list of all these things. When you build it up with that pipe operator, it puts all those in. That's the order that they'll be called in. And so put next, the framework just says, it literally looks at the very next thing. The internal implementation is that it has a class called provide, I think, a nested class called provide that takes a template parameter that is a size t, the index in the tuple of all these things. It basically internally keeps all these things as a tuple. And whenever you call put at the beginning, it says, I want to dispatch to 0. And so it goes and grabs the tuple at index 0 and says, can I call put on you? And if I can't, it increments that thing from 0 to 1. And then it tries on the next index. And if it can't, it increments from 1 to 2. Once it can call it, it calls that one and it's done. And so once you are running, if you don't do anything, right? So in here, if it's an S, we're gonna call put next. If it was something else like the debug packet and here we don't implement it, it wouldn't do anything. And that would be the end of the execution. Okay? Does that answer your question? Did I help you guys or did I confuse you? Okay. So the framework is doing a lot behind the scenes. But it's giving us this ability to write code that is composable and testable and very loosely coupled. So we look at the next thing, and we've got this compressed soup TCP. What about supporting that compressed version? Well, we can write a short module, call it zlib uncompress. It just takes some bytes. You give it something, if you give this thing some bytes, it's just gonna take them. And it's just gonna call whatever the inflate stuff is, right? You have to have one of these Z-stream things, and then you have to call inflate. The reason I know that you have to do this is because this is the extent of the documentation inside of that they gave you on what you're supposed to do. So I imagine using zlib is just like using zlib, but that's it. So basically in here, we will inflate, we'll uncompress this into this buffer, and then we'll call this make bytes, which given this stream, it will go and make a bytes and put it to the next guy, okay? And then what do? We do that, that's all, right? We added a feature of compression and we didn't change any code. We just added something because we added a feature. That's kind of the goal, right? Now, you can say, well, that's pretty simple. You probably could just go in and put an if this flag and go do this, and yeah, you can. But then what you start getting into is you start creeping all these different features and you start making your code much more tightly coupled. It's much less cohesive. Cohesive is simple. Do one thing, test it. If you have to write a bunch of tests for something, for all these different conditions, you know that it's too big. It's doing too much. So this is compressed. So now we've got that one. We should be able to get through this a little bit quicker just because we've established most of the rules. But again, ask me any questions. I want questions. There's two reasons I want questions. Number one, I want to make sure you understand what I'm talking about. Number two, I want you to get in touch with me and say, Jody, you're an idiot. This thing doesn't work. Here, look at this example, right? Yes?
I really like the composability. Just one question is around how do you make this zero copy, zero allocation, yet still have that composability? Can you do it with this framework?
Yeah, so what happens is this is actually, somebody asked me before, how does this relate to senders and receivers? And at the time I hadn't read the paper. It's similar to when you're building up something for senders and receivers, except what they do is they don't do anything, right? Here, you're actually building the whole entire thing, but it's not doing anything either as far as sending. But if you noticed on one of these, message parser has state. So when that happens, that constructor will get run at that point in time. At the point in time that it gets added, when this guy gets instantiated, right? You can say decal type of this and nothing will happen. But once you assign it to something, now a tuple actually gets created inside the framework, and each one of those tuples is basically, each element of the tuple is one of these. So internally the tuple will have 4 elements and it'll be those 4 things. And you can compose these together. So if you add one together, it'll just add that thing onto the end and call its put and they'll act as if they were one. Does that answer? Yes?
Does this tuple live in the head?
I'm sorry?
Does this tuple that you said you create, does it live in the head?
This head is not, this head is just an enum. It's just an opaque type, just so I can have the DSL of this. It just constructs it. It just sets up all the construction. The tuple lives in soup. This variable that you create, the tuple lives in there. Yes?
As far as I understood this, this is a kind of types and filters architecture, right?
Yes.
And what happens when your message is only halfly done, and then you have an error? How do we deal with this thing?
Yes, so error conditions are something that's, it's different. So you actually have several different ways. You can say that you want an exception to occur, right? Or you can say that you want an error to propagate backwards. These streams are actually dual. You can actually, you can put other, which basically says, put this to the other side of the queue and send it back up, okay? Or you can just send it on down the line and let somebody else deal with it, right? It's kind of like logging, right? What do you do with logging? Well, everybody has these loggers. Oh, I need to have access to a logger, so I have some static logger, or my logger has to be injected so that I can log something. Well, if you want to log something here, you just create a log message and send it down the line. If somebody wants to log something, they can put a logger module in there, and it'll intercept all the logging calls and do all the logging. Or it'll put it on a queue and have the logging be done in the background. But if there's no logger there, you pay no cost because there's nobody there to take the log message, right? So error handling is complex. I don't deal with it here because it is complex, but you can throw an exception. You can have the exception propagate. You can have the exception dismantle the stream. A lot of times if an exception occurs, you probably don't want to do anything because you're probably in the midst of doing some protocol. Or you can just you can return it, you can throw an exception, or you can send it downstream. Yes?
I may be confused, but is this like creating a big lookup table where the content of the message is then selecting a function that processes that?
You could say that, but the lookup table is done at compile time.
Yeah, so the template creates a lookup table in the background, which then directly goes to the function.
Yeah, it actually doesn't create a table. What it does is it does a recursive call. Literally what it does, when you call put to the first thing, it says, I want to call put on, it calls std get of 0 to see if I can call put on that thing. And if I can't, then it'll call std get of 1 to see if I can call put on that thing. It does it in a recursive manner, and there's some tricks because there's things I have to do, but that's basically what it does. It just algorithmically iterates over each one of the tuples until one of them accepts it, or until it gets to the end. And you can put something on the end that is a guard that says, I don't want anything to fall off the end, and create a compiler error if stuff falls off the end, right? And one of the things that you didn't ask, but it comes up is, what about, making sure I can only plug, squares into squares? Well, the fundamental theorem of this architecture is that you can pass anything to anybody, because if they don't understand it, they'll pass it to somebody else. So what you do is you can put guards at different places in the stream that will static assert if certain things happen. And the framework itself knows whether it's passed something interleaving or not. And if it reaches one of those, it'll just assert because it's an invariant that you've posted. So that's how you get around that. But you do have this dynamic flexibility that you could get things in the wrong order, right?
Just to clarify, the soup up there, the type of that is framework, angle bracket, those four things, and some new things.
Something like that. Yeah, it's a framework stream with a template variadic arguments, and underneath it's got a bunch of wizardry implementing it. But that's what this is. Yes, this is basically a framework class that holds a template of all those things. Holds a tuple of all those things. Anything else? All right. Well, let's see how far we can get. I'm glad we got questions here. So we want to try and do some moldy stuff. Well, mold is UDP. This is what they send you. Basically, they send you a header with a session ID and a sequence number and a message count. The sequence number basically says, here's the sequence number of the first message in this packet. And this packet contains, some number of messages. So this packet, the first sequence number in this packet is 42, and it contains 20 messages, okay? And then it has a session. The reason it has a session is because it identifies, the session. It identifies what all messages go along in the same session, and these sequence numbers are dependent upon the session, right? So you could have sequence number 42 in session 1 and sequence number 42 in session 2, and they're completely different, okay? So what we're gonna do is we're gonna parse the UDP packet. So the first thing we're gonna do is see if we have space for it, right? And notice here, we have this will only be active if we've got a mold UDP 64 protocol packet. We take our framework context and our bytes and our multi thing. If we don't have enough data, we just return. You could do one of the error handling things if you wanted. Here we basically pull the pieces out of the header. The thing that we didn't read earlier is that this protocol is funny. It says, hey, message count tells you how many messages there are, unless message count is 0. If message count is 0, it means it's a heartbeat. And the sequence number is the next heartbeat that you should get, right? The next expected heartbeat. Or unless it's FFFF. If it's FFFF, it means this is the end of the session, right? So, enough said. But if not, we basically, if it's not a heartbeat and it's not an end of session, we basically remove the prefix off, and we put next the header and the payload. Here's the header, here's the payload. The reason that we do the header and the payload is because you won't see the performance implementation here, you'll just see a simple one. But what happens is, normally you'll do you'll arbitrage, you'll get UDP packets on one channel and you'll get UDP packets on the other channel, and they guarantee that you'll get the same messages, but they don't guarantee that the packets will be framed the same. So you might get a packet on channel A that has messages 50 through 70, and you might get a packet on channel B that has messages 60 through 90, right? And so they overlap, which is a problem if you're trying to detect if you've missed something or not. Okay. Or we just put a sequence message of in session and a sequence message of administration session, giving the sequence number that we have. We can write a module that will split things into multiple messages, right? It'll split our payload. We grab our sequence number, we basically just loop through here, and we will put the very next sequence number. Now, this is not optimal. I do not recommend that you implement this, because basically what this is doing, it's taking, I've got 20 messages and I'm gonna call each one. Well, it might say I've got message 42 through 62. And you might have already processed message 60, you're expecting message 63, right? Normally what you do is you would do a range, but that code got a little bit more complicated than I wanted to put on a slide. So we basically do arbitration. And this is a very simple arbitration where we come through and we check to see, is the sequence number the one that I'm expecting? If so, I increment my expected and I put the message out, right? What happens is you might lose messages, they might come in order, but you're pretty much guaranteed that if you're doing A and B arbitrage, you're gonna see the same message always at least twice, right? Unless you've dropped it. So I'm at message 42, I see message 41. I drop it, I don't even need to do anything with it, right? If it's greater, then what we're gonna do is we're just going to, again, this is not how you would do it in production, but we're basically pretending like if I see a gap, I'm just gonna skip it, let you know I skipped the gap, and keep processing, okay? Normally what you do is you would detect the gap for mold. You basically send a UDP packet to their server. They will respond back to the same port that you sent the request on with a response. You can say, I need 1 million messages, and they'll say, starting at message 12. Great, I can fit 20 messages in there, here you go, And they'll send you one packet back with as many as they can stuff in it. And so that's how you can kind of get replays if you've missed them. But then we end up with this. There's our mold. There's our head. We have our mold protocols. We parse the packet. We split the payload. We do our simple ARB. And then we've got the dispatch, which is the exact same as what we had earlier, right? We don't need anything else different. And then we've got all the rest of the stuff. Because what do we do after this? Well, we need to do normalization on the messages so that when you read stuff from NASDAQ and NYSE and BATS and these certain places, that they at least look the same, so you're not having to process these specific messages. You might have a place that's actually going to build an order book. You might have a module that has a pub sub model where people can subscribe to get callbacks. You might have a module that basically says, I want to put these onto a message queue for somebody in another process to have. And so you can add those. You want to add those features? You write that one feature, you write the module, you compose it in, right? That's really, to me, that's the killer for it, right? Except that we could always do that, but we had to pay the performance. Now we can do it, and it's all compile time.